You're gonna solve, help us please solve this computer pizza. You doing road rage?
I'm road rage.
You're doing road rage. Road rage.
Oh, we're doing road rage. Let's go.
Oh, we're doing, I like to say, we're doing road rage.
We're doing road rage.
Suppose that the engineer software.
You want us to stand with them? No, I do not.
You wanna,
Let's get morals.
come over here so they can explain to you what's going on?
They can stay there. Okay, we got a crazy temple grad. All right, flying off the bridge. And it's our job to determine whether she is lying or telling the truth. So we're given a few pieces of information. To start, she testifies that she was traveling exactly 110 kilometers per hour. And since I guess we'll go into the assumption that assume she's innocent until proven guilty, even though she's a temple grad. So we'll assume. So the way I went about this is I assumed everything she said was correct to see what kind of what that would give me as far as how far she landed off the bridge, and then compare that to what actually happened to see if she was. So a couple things that can I have a Sharpie or something? Not a Sharpie, but dry erase board.
These are better than all this right now.
You're given some piece of information. So she said she was driving 110 kilometers per hour, which is approximately 30.6 meters per second. Just doing conversions. Then she slammed on her brake for exactly 1 second, slowing down before she hit the guardrail, broke the guardrail, and landed in the river 10 meters below. So her initial velocity, 30.6, just to kind of get the diagram. I just do a big clip in essence, even though it's water. They said that the bridge height was 10 meters tall. Here. That's the distance vertically the car dropped off the bridge. I'll say this, the speed of her car is 30.6 meters per second here. Once she slams on her brake, let's say the second from here, that'll take us from here to about here. This is the time of 1 second where she is braking. Brake. That's all right.
Yeah.
Good. She was braking here, so that's going to give her a velocity here after she braked. And then there's another change in velocity. They tell you that when you go through a guardrail, apparently if it's in great condition, your speed reduces by 10 meters per second. So whatever her speed is here, it's going to be 10 meters per second less here once she breaks through the guardrail, which is right here. And then that'll finally be her projectile velocity, her horizontal velocity off the edge of the bridge. So they tell us, the police tell us that you get an acceleration in this period of negative 8.83 meters per second squared, which tells you that if she breaks for a second, she's going to be traveling 8.83 meters per second less here than she is here. For 1 second, she'll be slowing down by 8.83 meters per second, which puts her at 21.73 meters per second approximately. And then they tell us that you are 10 meters per second less fast after braking through the guardrail, which puts them at 11.73 meters per second, which is her horizontal velocity coming off the edge of the bridge. So then she'll be a projectile until she crashes here. And so then what we solve for is this distance x, and if this distance x matches up with the distance the crime scene actually has, then she'll be innocent. If it's different, then she's guilty. She was actually traveling at a different speed. So we're going to figure out, since this is a horizontal velocity, it's not affected by gravity, so you can simply use distance equals rate times time if you're talking about the x direction. Since we know her rate is 11.73 meters per second, in order to figure out the distance x, you need to figure out time. And so to get time, you look at the vertical distance, the distance y that the car drops. which is affected by gravity. So we can use the equation that Dr. Hotte gave us, 1/2 gt squared. It's a 10-meter distance, 1/2 of 9.81 meters per second squared. Since initially she is starting from rest, vertically speaking, I guess. T squared, solving for t, which would be the square root of twice 10, 20 divided by g, 9.81, which will give you 1.42 seconds. So you can plug this up here, 11.73 meters per second times 1.42 seconds, and that gives you a horizontal distance of 16.75 meters. Is that right? Yes, 16.75 meters, which was approximately 16 centimeters according to this scale, right? 16 centimeters according to this step, because it was a 1-to-1 ratio. 1 meter equals 1 centimeters. So 16 centimeters, which if you measure the distance from the bridge to the car, it's actually like 26 centimeters. So she came up short according to that definition. So this does not equate to the actual 26 meters that the car actually was. So she was going much faster, which means she did not brake. She flew off the car going very fast, went further than she wanted. So she's guilty. Fell asleep at the wheel or whatever happens. That make sense?
Any comments? Questions? Differences of opinions?
Actually, if you redo that without the braking, it does land exactly what the car is.
So if she doesn't brake,
So if she
then
doesn't
it's the
break, where would
perfect
she land?
26 meters.
Yeah.
Because then all you get was the 10-meter reduction, which she'd be going to 20.6 off the edge.
So it
So
would,
the part where she's lying is that she braked.
so it'd be 20,
Because there was a road rage guy.
Yeah,
that caused her to brake,
28.5.
but apparently
20.5, yeah. I tried to make her about 30 centimeters from the bridge, but depending on how you measure it from the bridge, you're close. So there was enough of a difference that she did fall asleep at the wheel.
The only
She-
thing she was factual about was the 110 kilometer per hour.
Yeah, she was doing 110.
Yeah.
Thank you very much, good job. Okay. Who is doing crime scene 2 on the, crime scene 2?
Oh, that's us.
Okay.
Oh. I don't know, this is number 2.
Please explain what's happening in crime scene 2.
Okay, I'm gonna use the actual Scooby-Doo name, if you don't mind.
Scooby-Doo, can somebody erase this board?
I'll get it, because I'll be up there.
Well, the last person should erase it.
So, my man Fred took a bullet to the shoulder. Clean exit, and he, there's 3 shooters in the building, one of them carrying a 38 Special, one of them carrying a 357 Magnum, and one of them carrying a 45 ACP. And all of those bullets have different qualities, including muzzle velocities and bullet weights. So what we did is, first of all, we had to know a few things. When the bullet, can I just start with what I suppose the right answer is?
Absolutely.
Okay, so I suppose that the right answer is 38 Special.
Oh, no, don't start from there. You can't guess. You have to explain.
Well, I could start with any of them, right? So I'll start with 38 Special.
Okay.
How
All right.
convenient.
How convenient, right? I'm just guessing. I'm just going to start with 38 Special. So I have 38 Special with a muzzle velocity, which is the initial velocity, of 300 meters per second. And it changes, it is reduced after leaving a body to 30% of its original, So it's actually subtracting 70% of it. And let me find the velocity here. So it's actual, once it goes through his body, once it goes through Fred's body, its velocity that we're going to be calculating is 90 meters per second.
Is everyone okay with that?
I don't know how I call it.
If it solves the crime, we're okay with
Is that not correct?
It's correct. I'm just
Okay.
checking to see if someone else has a difference of
it. Our
opinion.
numbers.
What is your number?
We did it the right way, but.
Okay. All right, so,
All right, so that's the velocity that we're checking from Fred getting hit in the shoulder. Right here, it's leaving his shoulder at 90 meters per second this way. Okay, and it impacts the wall, which is a distance of 3 meters away from him. We'll just draw the wall right here. 3 meters away. And the bullet hits at a lesser level, a lesser height than his shoulder, which was .005. Yeah, .005. So the bullet hits .005 less than his body. So it's, wait a minute, I'm getting all jacked up here.
Who's with?
Hold on.
What's the units on that? 105 what, seconds?
No, .05 meters.
Okay.
Okay, I gotta write all this stuff out here.
Good idea.
90 meters per second. Distance X is 3 meters. Distance Y is .005. What else do I need to write down here? Oh, I have to have a time. So to solve for time, I know the velocity and I know the X distance. So I use the formula of this. Aaron, how do you learn to be so neat with your formulas? I just got them all over the place. 3 meters at 90 meters per second times time. And so when I figured that out, the time of travel came out to be 0.03 seconds. Is that right?
And that's the time of travel from where to where?
From the shoulder exit to the wall.
Okay.
0.03 seconds meters. Okay. So then once I did the calculation for my Y distance to find out if it actually equated to .005, Y equals 1/2 G T squared. And so I did, whoa, time out. 1/2 times 9.8 times 0.03 squared. And that came out to be 0.004 meters. Okay, so I'm a little short of my number there. But I got to do the other ones because they're like way off. When I came up with the other ones, their Y distance was, for the 45 ACP, it was .007 meters. So a little bit more than that. And for the 357, I didn't write it down. No, it's not. All right. So I never came up with .005, never once in any of my calculations.
Okay.
So my numbers were above and below .004 for
So
this
that was
one.
the closest.
This was the closest one that I came to.
So your conclusion is,
My conclusion is 38 special.
can anyone else tell us how they approached this? Is it a little differently? Could you explain how you might have approached it?
What we did was,
No, go up there and show.
I thought this was, did you really?
Yeah.
Huh?
Oh, we're,
Well, that's here.
okay.
That was nice that day.
Shoulder.
Here's the scenario, right? Enters the shoulder, it lands 3 meters away, going from a height of 1.63
1.325 down to 1.6275. That is a vertical drop equal to .005. Everybody, that's where the .005 came from. Okay, it's going to require so much time to fall that fast. Okay, so what I did next was find time to fall that far. So we use y is equal to 1/2 gt squared, 0.005, 1/2 of 9.8 t squared. I get a time of what Alan got, 0.03 seconds. Okay, that's going to translate to a certain exit velocity. Okay, so that next thing I did was find v exit, which you call Vx, which is fine. That's how fast it's going that way. So we took distance over time, distance of 3 meters, over time 0.03 seconds. I got the exit velocity at 100 meters per second. Okay, now they told us earlier in the scenario that the exit velocity, whatever it was, the exit velocity is 30% of the muzzle or entry. I call it entry, whatever came muzzle we're going in here, friction, whatever. So here's the exit, 0.3 V entry. We found the V entry to be 333 meters per second. And then we looked at the table. Which one most closely matches the 333 is the 300 meters per second. That's what we did. That way, we didn't have to do three different ways to figure out.
Very good.
Good.
You both had different approaches, you both got the right answer. Good job. Get promoted to detective. Good job. I know, my students often say, I'll solve a problem one way, and they'll say, well, I did it this way, get the same answer. We try to tell them, many times, there are many ways of approaching a problem. You do it, so, well done. I guess we can put that crime solved, right? And who do we arrest?
Janice Jackson.
Janice, geez, she's the one that keeps falling over.
Right.
And for extra credit, what happened to, what's Scooby-Doo doing?
Peeing on the cane.
Okay. Hotel jumper. Who's doing hotel jumper?
Want me to do the first part or the
You're
second?
gonna do everything except the follow-up? Please.
I got the original, I guess,
Can you
rather than the
step up
follow.
here and explain what happens?
think
The approach you took?
I think so.
Okay.
Let's see. Okay, starting with what we were given, which is that the body fell at 20, where shall I write?
Anywhere you like.
Oh, I got the marker here.
Oh.
I yell at my kids for playing it.
We know this, according to the examiner, that the speed when he hit was about 20.5 meters per second, right? We're given that. The first thing I tried to figure out was how long it took him to fall. So, T equals velocity divided by gravity, which is just spinning around, V equals GT, right? So,
Okay.
20.5 meters per second divided by gravity, 9.8 meters per second squared, is about 2.1 seconds. Okay? We just have 2.1
What is this
seconds.
first problem you're solving?
The time
No.
it took him
Wh-
to fall.
Why?
Well, because I need that in order to recognize how far he fell.
Okay, fine.
Okay?
Okay, just
Right?
check.
Okay, good. That's the first part. That's how long it took him to fall.
So he was in flight, how long?
Time to fall. 2.1 seconds.
Is everyone in agreement with that?
Yeah.
Who got this far?
Then we got,
Okay, thank you.
Okay, why'd I do that? Well, because we need to know how far he fell, and that leads us to this. Distance being 1/2 g times t squared.
So you're not taking it at face value that he was registered on the 4th floor?
Well, that's what we're trying to determine, right?
Okay, just checking.
That's what we're trying to determine, right?
Right.
Because that's where he was registered, but.
Right,
we're-
even though when they went to investigate, I think his room was locked and his balcony door was open, right? Everything?
Okay, but I'm not taking that at face value. The only thing I've taken as a given was that he fell at this rate.
Okay.
That he was going that fast when
Basically-
he fell. Everything else is a measured or calculated
Right,
quantity,
because,
okay?
because Dr. Pratt, you wouldn't question him. Oh, yeah.
I questioned everything.
Right.
he questions
We
everything.
questioned everything. All right, so now we have to figure out how far he fell. And we know this, half of gravity is 4.9. And we're multiplying that by what we had here, 2.1 seconds squared is 4.41 seconds squared. We'll knock that out. And what we're left with is the unit we're looking for, and that comes out to 21 meters. That's how far he fell. And using, using the conversion factor 3.1 feet, approximately to 1 meter, right? He fell about 67 feet. Okay? And using your conversion factor, that equals about, well, should I do that? That's by the conversion factor used, 20 centimeters divided by 10 feet, right? And that leaves us with 134 approximately centimeters, which if I go back to there, the scale model, leaves us somewhere between the 7th and 8th floor. Okay, I'm not sure, do you count that yellow portion?
No,
as
that's the lobby.
First floor?
No.
Oh, that's the first floor, okay. then
First
I'll
floor's
call-
the first.
The first floor is the windows,
Yeah.
then I'll call him falling from the 7th floor.
Does anyone else have that?
If you stop multiplying.
We're all in agreement, he came off the 7th. What was he doing up there?
Oh, no, well, yes, he was cavorting, and we'll prove that in a second.
I put down he's stupid.
He was cavorting. I don't know.
Okay, so he fell from the 7th floor.
He-
We still don't know what's going on
He
here.
fell, well, he did come off of the 7th floor, but he did not fall, which we will prove by doing this. I'm taking up a lot of space here, so I'm gonna go back. All right, now we have everything we need here. I think, since we know that, I measured this. I measured him about 110 centimeters. I'm not going to write the conversion I did, but 110 centimeters, and using the conversion factor, he landed about 55 feet from the building. Okay, and I can show you that if I want. I measure 110 centimeters times 10 feet divided
Okay.
by 20 centimeters, right? 55 feet. Why are we using that? Well, because of this. And here's where I might get a little bit confounded. Speed equals distance divided by time, if we're flipping that thing over. And that's what we need to determine. We know the distance at about 55 feet, which converts to about 17 meters. And we're dividing that by the time it took him to fall, 2.1 approximately seconds and that calculates to about 8.1 meters per second, which if we go to the table that was on the back, equates to about how fast he would be going if he was running out of the 7th floor window. He ran out the 7th floor window, trying to get the pool apparently, but overshot it, and he's dead.
So
So
this
he was
appears-
not pushed, he ran, or he was running from somebody, but he ran out the 7th
So
floor
it
window.
appears to be an accident, not a homicide?
Well, we don't know that yet, right? We don't know if he was running to find the pool or if he was running from bad guys.
Right.
We don't have enough information
So
for that.
on the follow-up, you have the follow-up. What do we have? Thank you, good job. You had a lot of moving parts on this one, right?
Yeah, it was.
Okay. So what is the follow-up? Can you explain to me what the follow-up is?
The follow-up, we're trying to determine if it's actually possible to jump from a certain height and land into the pool and actually make it.
Why is that? Everyone read the follow-up?
Because we want to see if he's actually going to, like, if it is like a homicide
So
or-
you know now that his friend that has now been interviewed says that Einstein was a good sprinter, and that matches with the chart, right? And an accomplished diver, right? And so he said he boasted he could make it to the pool below his hotel window, and Newton says, "You're crazy, you can't do it." From the 7th floor, Einstein tries it anyways and runs out. Go for it.
So now we're just trying to see what would be the actual distance that he would need for that pool. So just going back a step, just for like a visual. We knew before that he came out this way. X marks the spot, he landed here, and we need to see how much further away that pool was. And we measured this first one, this was the 110 centimeters. And our new measurement, a safe distance to get to the pool, was another one of, is it swimming pool? I'm not an artist. Our swimming pool was.
Yeah, that's what I'm asking you to do. She's part of your group, right?
It was the 10 extra feet. Okay, so now that we had that, we need to convert that over to meters. So that 10 feet, we took times. That was from our conversions from yesterday. Once we found a conversion, that equaled the 3 meters. More that he needed to jump outward to the pool. Okay, so then we did that, we added that to our distance back here. So if we took those, the 16.7 meters plus the 3 meters more that he needed for the pool, that yielded about 20 meters that he would need total. So now that we have our distance, we could find the time, because we have this velocity that was at 8 meters per second from our table. And we know our distance, our new distance, which is the 20 meters. And so now I can find time, that's the only thing left.
And what time does that represent?
That's the time that he needed to be able to be in the air to
Okay.
make that distance outward.
All right, and what is that value?
So when we solve for time, we're left with time is 20.5 seconds that he needed to be able to fall out. So now that we have that, we could plug it into the other equation that was given. 1/2 GT squared, and then we just plug in all of our information.
Sorry.
Let's see. And then we're left with what the distance that he actually needed to jump up here was the 30.63 meters. And we guess that that would be like more up on the roof instead of the 7th floor.
So it wouldn't have to be on the roof. Anyone get that point? Get that far? Very good, thank you. Okay, good job. So you were able to solve the 3 crimes. Congratulations. You're all in for bonus points and so forth. I enjoyed having you in this class.
Thank you, Eddie.
I hope you enjoyed solving the crimes. You weren't too frustrated. And some of you, I guess I will see during the follow-up or August follow-up. Who's coming back here for the August follow-up? Some, but not all. Okay. Look forward to seeing you then in a couple of weeks. Thank you very much.